Alright, welcome to the class. Today we're going to have a look at the second lesson of chapter 4, three-dimensional structure. Chemical bonds play an important role in determining the nature of various substances. So does the three-dimensional structure. Three-dimensional structure of a substances refers to the arrangement in the three dimensions of items that the substance comprises. Three-dimensional structure often helps determine how the pure substance will behave in chemical reactions. It also influences the interactions with other substances, especially in biological systems where reactions have to be efficient and highly specific. For example, enzymes, an important group of molecules in living organisms, interact with molecules primarily based on molecular shape or molecular geometry. Enzymes and molecules they act on interact in a manner similar to locks and keys. You cannot use just any key to open a lock. The ridges and shapes of the key must be complementary to the shape of the inside of the lock. Receptor proteins on the surfaces of cells function very much like a lock. A specific molecule, such as a hormone or a neurotransmitter, must fit perfectly in the receptor pocket before it will signal the cell interior. At the cellular level, communication, growth, defense, and differentiation all ultimately depend on molecular shape. Beyond the cellular level, entire organisms can communicate through a process called semi-chemical communication, where chemicals act as messengers to relay information from one organism to another. For example, queen bees secrete a unique chemical, or pheromone, to prevent worker bees from repelling. Okay, next we're going to have a look at a very important theory which is called VSEPR theory. Many sophisticated and highly accurate methods such as X-ray, crystallography, and nuclear magnetic resonance or NMR spectroscopy exist for determining three-dimensional structure. We must see these methods when we need precise information about molecular structure. But they require lengthy experiments and expensive equipment. However, we can predict the approximate structure of a molecule or ionic compound using the VSEPR theory, which is valence shell electron-pair repulsion theory. The main idea behind the VSEPR theory is that you can determine the structure around an item by minimizing the repulsive force between electron pairs. Remember that the electrons are all negatively charged and thus repel each other. Items can share electron pairs in a covalent bond and can also have lone electron pairs that do not participate in chemical bonds. We have already seen examples of this in the previous lesson when we draw the Lewis structures, right? According to the VSEPR theory, bonded and lone pair electrons position themselves as far apart as possible in a molecule to minimize the repulsive forces between them, a concept called electron-pair repulsion. So, to illustrate the VSEPR theory, consider beryllium chloride, or BeCl2. Beryllium chloride is rather unusual substance. It's a molecule, not an ionic compound. Although covalent bonds typically occur between items of nonmetals, in beryllium chloride, covalent bonds occur between a metal item and a non-metal item. So we will learn more about how this happens in the next few sections. Beryllium chloride can be represented by the following structural formula and ball and stick model, which is shown here on top left. Note that there are two bonding electron pairs around the beryllium atom. What geometric arrangement of these electron pairs allows them to be as far apart as possible to minimize the repulsive forces between them? The best arrangement is to place electron pairs on opposite sides of the atom, or 180 degrees apart. Now that we have determined the optimal arrangement of the electron pairs around the central atom, we can specify the three-dimensional structure of beryllium chloride. Since the beryllium atom shares each bonding electron pair with the chlorine atom, the molecule has a linear structure with 180 bound angle. Next, consider another compound, boron trifluoride, or BF3, which can be represented by the following simplified Lewis structure. See the graphs in the middle. In this Lewis structure, three bonding electron pairs surround the boron atom. So again, ask what arrangement will minimize electron pair repulsion. The bonding electron pairs are the farthest apart at an angle of 120 degrees in a two-dimensional plane. Since the boron atom shares an electron pairs with each fluorine atom, the three-dimensional structure can be represented as the graph here. Graph in the middle. The shape of this molecule is planar or flat and triangular, and it's described as a triagonal planar structure. Next, consider another compound, methane molecule, or CH4, which can be represented by this structure formula, which is shown here on bottom left. There are four bounded electron pairs surrounding the central carbon atom. Again, what arrangement of these electron pairs minimizes the electron pair repulsions? First, try to arrange the molecule into a square planar arrangement where all four bonds lie in the same plane. In this arrangement, the carbon atom and the electron pairs are centered in the plane of the paper or the screen, and angles between the electron pairs are all 90 degrees. And also note that there is another arrangement that would put the electron pairs even further away from each other. The tetrahedral structure has an angle of about 109.5 degrees. Well, actually, you can prove this with some mathematical methods. The angle is around 109.5 degrees. This concept is illustrated in the figure on the bottom right. So try to prove that by yourself after this class. And the atoms are equally positioned in four locations around the central atom. This arrangement can be represented by the following structural formula and ball and stick model. Any questions? So this three-dimensional arrangement allows the maximum possible separation of full pairs of electrons around a central atom. In the structural formula for the methane molecule, some bonds are represented as dashes or wedges to better communicate the arrangement of the atom. So on the left side, Table 1 summarizes the conventions for representing the three-dimensional arrangement of atoms in structural formulas. Blue lines were added to the ball and stick model of methane on the previous slides as shown here. To emphasize the tetrahedron, where whenever 4 pairs of electrons are present around a central atom, always place them at the vertices of a regular tetrahedron. Okay, recall from section 4.1, previous section, we have learned yesterday that the central atom of the phosphorus pentachloride, or PCl5 is overfilled, right? There are 5 covalent bonds between the phosphorus atom and the 5 chlorine atoms. In this case, the geometric structure that minimizes electron repulsion is a trigonal bipyramidal structure. In a phosphorus pentachloride molecule, the 3 phosphorus chlorine bonds are in the same plane and 120 degrees apart from each other, and the remaining 2 bonds are 90 degrees from these bonds and 180 degrees from each other. So this concept is shown here in figure 2a. Similarly, sulfur hexafluoride, or SF6, forms 6 covalent bonds. The predicted VSEPR series structure for this molecule is a octahedral structure. In this structure, the 4 sulfur fluoride bonds are in the same plane, separated by 90 degrees angles. The other 2 sulfur fluoride bonds are perpendicular to this plane, one above it and one below it. And this concept is shown here in figure 2b. So, to put this in a summary, the VSEPR theory helps us to determine the arrangement of electron pairs around a central atom that minimizes electron pair repulsions. The lone electron pairs surrounding non-central atoms do not play a role in determining molecule shape. However, when a central atom has 1 or more lone pairs of electrons, the geometric structure of the molecule and the positions of the surrounding atoms are affected. For example, if we consider ammonia, whose molecule is NH3, which has a single lone electron pair on the central atom, which is shown here on top left. We might predict this molecule has a tetrahedral structure because there are 4 pairs of electrons around the central nitrogen atom, right? However, the lone electron pair repels a little more than the bonding pairs, and thus pushes the bonding pairs closer together. As a result, the bond angles decreases from 109.5 degrees to 107 degrees. This forms a trigonal pyramidal structure because the central atom is the central atom is a vertex of a pyramid with a triangular base, which is shown here in figure 3. Note that the 3-dimensional structure classification depends on only the spatial arrangement of the atoms bounded to the central atom. Although the lone pairs strongly influence the angles between the bonds and thus the structure of the molecule, the lone pairs are disregarded when describing the overall shape of the molecule. For example, if you consider water, or H2O, its low structure is as shown here on bottom left. Ignoring the lone pairs around oxygen, we would predict a linear structure, right? Like beryllium chloride. However, the lone pairs of electrons on the central atom repels bonding pairs, thereby decreasing the angle between them. If you place the bonding and non-bonding electron pairs around the oxygen atom as far apart as possible, the structure will be tetrahedral, as in methane. However, in the water molecule, the two lone pairs of electrons repel the bonding pairs with more force, making the hydrogen-oxygen-hydrogen bond angle 104.5 degrees instead of 109.5 degrees. And the result is a V-shaped or band structure, illustrated in figure 4. And common three-dimensional structures predicted by the VS-EPR theory are summarized here in this table, table 2. Spread out all over these 3 pages. You can have a look at the pattern after this class, okay? Total number of electron pairs could be either 2, 3, 4, 5, and 6. And correspondingly, the number of lone pairs could be 0, 1, 2 for each number of the total number of electron pairs. Okay, so next, let's have a look at the common steps we can use to apply the VS-EPR theory to predict the structure of a pure substance using this theory, which is summarized here. The first step is to draw the simplified Lewis structure. Then count the electron pairs surrounding the central atom, including both bounded and lone electron pairs, and arrange them in a way that minimizes electron pair repulsion. Do this by putting the electron pairs as far apart as possible in a three-dimensional space. And then step 3 is to place the atoms bounded to the central atom at the ends of their bounded electron pairs. And last, determine the name of the structure from the positions of the atoms and lone pairs of electrons. Okay, now let's see a example to illustrate how we can predict the structure of a substance using the step-by-step VS-EPR theory. Okay, let's consider a sample problem here. Predict the structure of carbon tetrachloride or C4L2 using step-by-step VS-EPR approach. So I'll give you some time to consider this question by yourself, and after that we'll have a look at the solution together. Okay. Alright, let's have a look at the solution together. So in the first step, we can draw the simplified Lewis structure, right? We have learned this in yesterday's lesson. And in step 2, count the electron pairs surrounding the central atom and arrange them to minimize electron pair repulsion. So in this molecule, the carbon tetrachloride has 4 pairs of bounding electrons around the central atom. There are no lone electron pairs on the carbon atom, right? So the best arrangement of the 4 bounding electron pairs around the central atom is a tetrahedral structure. And then in step 3, we can place atoms bounded to the central atom at the ends of their bounded electron pairs. So this structure is a three-dimensional structure of the carbon tetrachloride. Can you see that? Also remember that we can use some dashed lines or the triangle lines to represent the three-dimensional arrangement of the item in structural formulas. And the last step, we can name this. We can then name this three-dimensional structure, which is a tetrahedral structure, right? Did you get it? Alright, if no questions, let's have a look at another problem. Predict the structure of an ammonium ion, NH4, with a +1 charge, using the step-by-step VSEPR approach. Alright, let's have a look at the solution together. Again, first step is to draw the simplified Lewis structure for the polyatomic ion, which is shown here in top right. Then we can count the electron pairs surrounding the central atom and arrange them to minimize the repulsions. The ammonium ion has 4 pairs of bonding electrons around the central atom. There are known lone electron pairs in the ion. The best arrangement of the 4 bonding electron pairs around the central atom is tetrahedral. Then, in the next step, we can place items bounded to the central atom at the ends of their bounded electron pairs. And in the last step, we can then name the three-dimensional structure. The ammonium ion has a tetrahedral structure as well. Okay, if no questions, let's have a look at another problem. Predict the structure of phosphane, or PH3, using the step-by-step VSEPR approach. Okay, I'll give you some time to consider this problem by yourself, and then after that, we'll have a look at the solution together, okay? Alright, now let's have a look at the solution together. First, we can draw the simplified Lewis structure for the molecule, which is shown here on the graph on top right. Then Count the electron pairs surrounding the central atom and arrange them to minimize repulsions. The phosphine molecule has 3 pairs of bonding electrons around the central atom. There is 1 lone electron pair on the phosphorus atom. The best arrangement of the 4 electron pairs, 3 bonding and 1 lone pair around the central atom is tetrahedral, right? Then we can place items bounded to the central atom at the ends of their bounding electron pairs. So if we have 3 bonding pairs and 1 lone pair, the 3-dimensional structure is a trigonal pyramidal. And this is shown here in the figure on the bottom right. Okay, so here is a summarized cheat sheet that you can use to help you to decide the 3-dimensional arrangements according to the VSEPR theory. Also, this theory applies to multiple bonding as well. So we'll talk about multiple bonding cases later, okay? So have a look at this cheat sheet and probably want to write this down on your notebook. Alright, next let's have a look at the VSEPR theory and the molecules with more than 1 central atom. So far we have investigated pure substances that contain just 1 central atom surrounded by other atoms. Many other have more than 1 central atom, right? You can still use the VSEPR theory to predict the 3-dimensional structure of these more complex molecules. For example, consider methanol or CH3OH, which has 2 central atoms, carbon and oxygen. Methanol can be represented by the following simplified Lewis structure, which is shown here on top left. We can predict the 3-dimensional structure from the arrangement of electron pairs around both the carbon and oxygen atoms. In the molecule or ionic compound with more than 1 central atom, we first need to predict the arrangement of electrons around each atom individually. Then combine these arrangements to predict the overall structure. There are 4 pairs of electrons around the carbon atom, so it has a tetrahedral arrangement, which is shown here in figure 5a. The oxygen atom also has 4 electron pairs, 2 bonding pairs and 2 lone pairs. So it too has a tetrahedral arrangement. The oxygen atom has a slight distortion of the tetrahedron because of the space requirements of the lone electron pairs. So the 3-dimensional structure around the oxygen atom is bent, which is shown here in figure 5b. The overall geometric arrangement for the methanol molecule is shown here in figure 5c. Okay, next let's have a look at a sample problem which illustrates this concept. Predict the structure of methylamine or CH3NH2 using the step-by-step VSEPR approach. Okay, let's have a look at the solution together. So in step 1, we can draw the simplified Lewis structure. There are two central items in this structure, carbon and nitrogen, right? So we can count the electron pairs surrounding the central item and arrange them to minimize electron pair repulsion. The methylamine molecule has 4 pairs of bound electrons around the central carbon atom and 3 pairs of bound electrons around the nitrogen atom. There's also 1 lone pair of electrons around the nitrogen atom. Both central atoms therefore have a tetrahedral arrangement. Okay, in step 3, we can then put the atoms bounded to the central atom at the ends of their bounded electron pairs. This concept is shown here in the figure on the bottom right. In the last step, we can name the 3-dimensional structure. The carbon atom in methylamine has a tetrahedral arrangement of atoms, and the nitrogen atom has a trigonal pyramidal arrangement of atoms because it has 1 lone pair of electrons. So this example shows the cases how we can use the VS-CPR theory to predict the arrangement of molecules with more than 1 central atom. Okay, next let's have a look at the cases where we have multiple bonds. So before we dive into that concept, again, first make sure you are familiar with the concept shown here in this cheat sheet. This is how we can use a VS-CPR electron pair to predict the electron pair. This is how we can use VS-EPR electron pair arrangements to predict the associated molecular shapes. And actually this also applies to multiple bonds. Molecules or ionic compounds with double and triple bonds have different chemical properties than those with single bonds. For example, hydrocarbons with double or triple bonds react quickly with bromine or potassium permanganate, whereas hydrocarbons with single bonds react much more slowly. Double and triple bonds are shorter and stronger than single bonds between the same types of items. However, pure substances with double and triple bonds behave very similarly to pure substances with single bonds when it comes to 3-dimensional structure. In a double or triple bond, there's more than 1 bounding pair of electrons. When using the VS-EPR theory to determine structure, we must place all of the multiple bonding electrons together. Okay, we'll use an example. We'll use example problem to show this concept. So let's consider this sample problem here. Predict the structure of carbon dioxide, or CO2, using the VS-EPR approach. Again, I'll give you some time to consider this by yourself, and after that, we'll have a look at the solution together. Alright, let's have a look at the solution together. So in the first step, we can draw the simplified Lewis structure for the molecule. In the carbon dioxide molecule, carbon is the central atom, and it's bounded by double bonds to each oxygen atom, right? Which is illustrated in the figure on the top right. Here. Then in step 2, we can count the electron pairs surrounding the central atom and arrange them to minimize electron pair repulsion. The carbon dioxide molecule has 4 pairs of bounding electrons around the central atom. Each carbon-oxygen bond is a double bond that consists of 2 pairs of electrons. For the purpose of VS-CPR, treat a multiple bond as a single group of electrons. In effect, we are counting the number of bounded items. There are 2 items bounded to the central carbon. Therefore, the shape is linear. The generalization outlined in the previous table we see still apply to multiple bounding if we count items bounded to the central item rather than electron pairs. Then in the next step, we can determine the positions of the items. Place items bounded to the central item at the ends of their bounded electron pairs. And finally, we can name the 3-dimensional structure. The carbon dioxide molecule has a linear structure. Since each oxygen item forms a double bond with a carbon item, the configuration that maximizes the separation of electrons is a linear shape. The electrons are 180 degrees from each other. Do you have any questions? Okay, good. Well, actually, the VSEPR theory works well for most molecules and ionic substances that contain non-metallic elements. However, there are exceptions. The theory fails in a few instances. For example, phosphine, pH 3, has the same Lewis structure as ammonia, NH3. Trigonopyramidal. From the VSEPR theory, we would expect phosphine to have the same bound angles as NH3, 107 degrees. However, the bound angles of phosphine are actually 94 degrees, which is shown here in figure 6. So, how does this happen? There are ways to explain this difference, but we have to add more rules to the theory. This example illustrates that simple theories are likely to have exceptions. The amazing thing about the VSEPR theory is that it correctly predicts the structures of so many pure substances. So if you want to use this theory to predict the structures, be careful with these exceptions, okay? Alright, so this is pretty much about today's lesson, and I hope you learned something today. Remember to complete your homework, which you can find from Google Classroom, and submit them before the deadline, okay? I'll see you next time. Bye.